this is an example of using the gas laws to predict the changes expected in P, V, N, or T. The problem we have is problem 612 from your textbook, and it says that a balloon is filled with helium, and it tells you when the following changes are made at constant temperature, which of the diagrams, A, B, and C, shows the new volume of the balloon. Well, one of the ways that you can look at this is to look at all the possible variables, which are P, V, N, and T, and decide which of those variables are being held constant. When it says that the balloon is filled with helium gas, you typically want to consider that that means that the amount of gas is constant. We're going to consider that the balloon is a closed container and we are not adding any gas to it. It also specifically says that you are using a constant temperature. Again, you don't know what the temperature is, but it doesn't change, and that's what's important. We have an initial volume. We don't know what it is, and since we are going to be looking at the new volume, it might be easier just to call that initial volume 1. There's no units being put with it. We're just going to use this for comparison. And we're going to do part A, and it says that the balloon is floating to a higher altitude, where the outside pressure is lower. So we want to start with some initial pressure, and again, it might be just easier to put a pressure of 1 here. Again, since we're just looking at changes, we're not going to put any units in this either. Now, what we are told is that the pressure is going down. So I'm simply going to put an arrow down here, and I am asked about what happens to the volume. So when I put in the relationship between P, V, N, and T, P times V is proportional to N times T. T and N are constant. I know that my pressure is going down, and what I expect with this is the inverse proportionality, the volume will go up. So if the volume goes up, and here is my initial volume, I would expect my final volume to be larger and look like this. So notice I haven't had to do any math in this process. I'm simply looking at direction. So my answer for this would be the direction is that the volume is increasing. And I can put a circle around that because that is my answer to the question. So I can see the difference between where my answer is and where my given information is. So no math this way, but just using the relationship. If we were looking at PV, or if we were looking at P and T with pressure and temperature constant, if pressure went up, we would expect temperature to go up. So you can look at this as a fence. If both of your variables that are changing are on the same side, this is an inverse relationship. If the variables that are changing are on opposite sides, it will be a direct relationship. What I want to show you here is the difference between a mass-volume solution and a mass-mass solution. In this case, it tells us that we have 2.31 grams of sucrose dissolved in a total of 25 milliliters of solution. Multiplying this times 100% will give us the percent sucrose. So we're going to take 2.31 and divide it by 25, which equals, whoa, that's not right, 2.3, let me clear it, 2.31 divided by 25 equals, times 100 would give us 9.24%, And if I just said 25 milliliters with two significant figures, that would be 9.2%. Now, in this solution, you'd take 2.31 grams and you would put a little bit of water in, get it into solution, and then dilute it up to 25 milliliters in a graduated cylinder. On the other hand, if we were going to make 25 grams of solution, we would actually be measuring the amount of water we add, not the total volume of the solution. So if my total solution is going to weigh 25 grams, and 2.31 of those grams are going to be sucrose, I'm actually going to subtract. So I would have 25 minus 2.31, and that is actually 22.69 grams of water. Now, my percentage is actually going to be the same, but now I'm going to have 2.31 grams of sucrose, and I'm going to have 100 grams of solution. Whoops. I'm going to have 25 grams of solution. Get rid of that. We're going to have 25 grams of solution and multiply that times 100%. Still going to get the 9.24% sucrose. But notice here, I know exactly how much water I'm going to add, and I know how much my solution weighs. In this case, I really didn't know how much water I was putting into the solution.